Hello, welcome to session number 13 in the series Analog Circuit Design using ADS. This is Anurag Nigam. Last time I demonstrated a high frequency response of a common gate amplifier, and we concluded that in a common source amplifier we are looking at two poles and a right hand side 0, and then we used compensation technique to move that 0 to first to infinity and then to a point in the left half of the S plane. And to stabilize it, we introduce that 0 between the first pole and the second pole. Now in common gate amplifier, with the derivation we have shown that there is only one pole, right? And the second pole occurs, that one pole is because of, so if you look at here, okay, so we have shown that there is only single pole here, and this pole is due to the output node, and then there is a second pole which will come to a very high frequency due to the input node, right? So when this RS is very small, that would be at infinity, right? So ideally it is not at infinity, but if RS is 0, it is the second pole moves to infinity. So this is what we discussed in case of a common gate amplifier, as you see over here. Now the next thing which I'm going to discuss is the frequency response of a two-stage OpAmp, right? So if you look at the schematic, okay, so I'm going to number these transistors. And the two transistors which are of concern to us, right? These two transistors are, so I can number this as 1, 2, 3, 4, 5, 6. So 4 and 6, okay, so 6 is going to be the load for the gain stage 4, right? So 4 is the one which provides the gain, and 6 is the load for that gain stage. And similarly, there is a common source here which is 7, and the load is 8. So load is going to be this one, and this current is the same as the ITL current over here. I out is same as ITL because transistor number 2 and 8, they are the same size. So if you can see here, this is 8 and this is 2, they are the same size. So just to keep in mind, 4 is the gain stage here with the 6 as a load, 7 is the gain stage here with 8 as load. So if you remember this numbering, so let's put here a model, right? So let me just put here a model. Okay, so the way to do it is, I am going to take this as a 4, which is going to be GM 4 times of V in. And by the way, this V in is going to be the differential in, okay? And then you have got R1, which is the parallel combination of RDS 4 and 6. And then you have got the C1, which is CGS1, right? And then CDB2 and CDB1. So this is the input node for the transistor 7, right? So this is VI, node VI. And then you have got the RC compensation. This is R and C compensation. And then you have got the output node. Output node, first thing is the GM7 times of VI. So this is going to be the current. And then you have got the R2. This R2 is basically due to GDS7 parallel with RDS7 parallel with RDS8. So that is going to be R2. And then there is going to be C2. And as I told you, two-stage op-amps are not loaded with resistance, right? They are going to be driving only capacitors. So in this case, you have C2, which would be CDB8 plus CDB7 plus CL. So let's write that down. So R1, or rather 1 over R1, is G1. So this would be equal to GDS 7 plus GDS 8. GDS 2 plus GDS 4 plus GDS 6. GDS 4 plus GDS 6. Okay, so I'm assuming that this transistor is 6, this transistor is 4. So GDS4 plus GDS6 is going to be R1, and C1 is going to be CDB4 plus CDB6, right, plus CGS7. Okay, so if you see, CDB4 is across here, CDB6 is across here, and CGS7 is across here. So this node, this particular node, is going to see that sum of these capacitances. So this is going to be the input node, right? Okay, next I am going to look at the output node. We have got G2. G2 is 1 over R2, which is going to be equal to GDS7 plus GDS8 plus GL, but GL is not there because RL is infinity. You don't load this OpAmp with a resistor. If you want, you can keep GL, but that's not what it's going to drive. C2 is going to be equal to CDB7 plus CDB8 plus CL, the load capacitance. So this is that. So this node is VO, this node is VI, and there is V in here. So let's write an equation at the output node. VO and whatever is connected to it, which is G2, right, plus SC2, right, okay, plus, sorry, G2 plus SC2 plus the conductance here. The conductance here is going to be 1 over R plus 1 over SC. So this is going to be the conductance connected that way, minus the adjoining node, which is VI, and that is going to have 1 over R plus SC, 1 over SC, right? And then the current which is flowing out is positive, right? So there's going to be plus VI times of GM7. That should be equal to 0. So that would give VO by VI equal to, so you can assume that, so that is going to be equal to, okay, 1 over R plus 1 over SC, because it goes to the other side, so this minus will become plus, and this plus will become minus GM7. This thing divided by G2 plus SC2 plus 1 over R plus 1 over SC. Okay, so this is going to be VO by VI. Now let's look at the input node. Input node VI times of conductance is connected, that will be G1 plus SC1 plus the adjoining node, right, 1 over R plus 1 over SC, right? So that would be there. Then the current which is going to be, so it will be minus the adjoining node, and in between you have 1 over R plus 1 over SC, okay, and then the current which is flowing out, okay, would be positive, right? So current flowing out would be positive, so you'll have plus of GM4 V in, right, GM4 V in. Now that will be 0. So now I'll substitute VO from this equation. So I'll substitute this VO from this equation, right? So I'm going to have VI times of G1 plus SC1 plus 1 over R plus 1 over SC. Okay, this is there. Then it will be minus of VI, and here it will be 1 over R plus 1 over SC, right? This is this term times of this, right? So that is 1 over R plus 1 over SC minus GM7 divided by G2 plus SC2 plus 1 over R plus 1 over SC. Okay, so this will be this plus GM4 V in, right? Yeah, so plus GM4 V in plus GM4 V in should be equal to 0. Okay, so now I can get VI over V in. Okay, so this VI over V in is going to be, so this will become minus GM4 coming to the right hand side, right? Minus GM4 coming to the right hand side divided by this term G1 plus SC1 plus 1 over R plus 1 over SC, this term minus, okay, so it will be a multiplication of this term, right? Okay, so it will be multiplication of this term, multiplication of this with this G2 plus SC2 plus 1 over R plus 1 over SC, right? Minus of 1 over R plus 1 over SC times of 1 over R plus 1 over SC minus GM7. So that is going to be there, right? So now VO by VI is this term, and I multiply this term with this term, correct? So if I multiply this term, okay, now another thing which has happened is there will be another thing which will come to the numerator, SC2 plus 1 over R plus 1 over S, 1 divided by SC. Okay, so now this is the thing which has to be multiplied with this. Okay, so VO by V in will be multiplication of two terms is equal to so in the denominator you have this, and in the numerator also you have this, right? Is it G2 plus SC2, right? So that thing would cancel out, isn't it? Right, so you will have just that. So what you will have is 1 over, so minus GM4 will be there, minus GM4, 1 over R plus 1 over SC minus GM7, right? And the denominator would be, so this thing cancelled out, right? Would be this term only. Okay, G1 G2 G1 plus SC1 plus 1 over R plus 1 over SC. Okay, G2 plus SC2 plus 1 over R plus 1 over SC minus of this thing 1 over R, 1 over SC times of 1 over R plus 1 over SC minus GM7. Now we have to simplify this one, right? So R plus, okay, so I have to simplify this. Okay, so let me see how to simplify this. Okay, so R1 R2, okay, R1 R2, G1 G2, okay, so now I'm going to open this denominator. So I'm just going to solve the denominator first. So I will multiply the thing with R1 R2. So what I do is I would put here R1 R2, and then I multiply both terms with R1 R2, R1 R2, and here I will do R1 R2, correct? So both terms are multiplied with R1 R2, right? So now I will multiply first term with R1, so I will be left, so I'm just solving the denominator one, right? So I will be left with R2 plus SC1 R1 R2 plus R1 R2 divided by R plus 1 over SC. So this would be, rather I will not multiply with R2 this term, just one second. So let's simplify this way. The first term I will multiply with R1, so I'll be left with 1 plus SC1 R1 plus R1 divided by R plus 1 over SC. And the second term I will multiply with R2. I'll be left with C2 R2 plus 1 over R plus, so it will be R2 1 over SC, right? Okay, so okay, let's continue doing it. So I'm not sure if I'll arrive at the right result, but I'm just going to do like other people do, the brute force stuff. R1 R2 by R plus 1 over SC times of 1 over R plus 1 over SC minus GM7, correct? So let's open the brackets. So I'll be left with 1 plus SC2 R2 plus R2 by R plus 1 over SC, and then I'm multiplying the second term, which is going to 1 C1 R1 plus S square C1 C2 R1 R2, right? And then I will do plus S C1 R1 R2, right, divided by R plus 1 over SC, and then the last term I'll multiply. The last term would be R1 divided by 1 over SC, okay, and then it will be SC1 SC2 R1 R2 plus SC2 R1 R2 divided by R plus 1 over SC, right? So this is all opened, minus I'll open this one also, so it will be R1 R2 divided by plus R1 R2 divided by R plus 1 over SC square plus, so this will be minus term, this will be a minus term, plus GM7 R1 R2 divided by R plus 1 over SC. Now this is the term, it's only one minus sign here. So if I was to multiply with this, there will be a square term here also, right? Because this is multiplied with this R1 R2 divided by R plus 1 over SC square, isn't it? Where is that square term? The last one. So R1, this one, okay, there will be a plus term of the last multiplication over here, right? This one with this one, right? R1 R2 divided by R plus 1 over SC square. So this term would cancel with that term. So now I'm left with this, right? Okay, so okay, if I was to multiply numerator and denominator by okay, let's see how much it will simplify. SC will come to the top, 1 plus RSC. Okay, so now what I'll do is, further simplifying it, I would have 1 plus SC2R2 plus, so I'm doing this here, okay, and this is SCR2 by 1 plus SRC. So it is going to be a little complicated, but maths is something which is like a, sometimes it's just a brute force. SRC plus SC1R1 plus S square C1 C2 R1 R2, right? Again this one would be SC will come to the top, S square CC1 R1 R2 divided by 1 plus SRC, right, plus R1, so it will be SR1C divided by 1 plus SRC, right, plus SC, so it will be S square C2C R1 R2 divided by 1 plus SRC, okay, plus GM7 R1 R2 SC divided by 1 plus SRC. Now if I take all the terms and if I multiply with 1 plus SRC, right, isn't it? Okay, so I will do that. Okay, I will have okay, so I will multiply everything with 1 plus SRC, isn't it? Okay, so I'll be left with 1 plus SRC plus SC2R2 plus S square CC2R2, right, plus SCR2 plus SC1R1. Let me see if I'm recording. Okay, this will be difficult for people to follow, right? Then you will have S square C1 R1 RC plus, this is going to be cube term, S cube C1 C2 C R1 R2, okay, plus the same term S square C1 C2 R1 R2. Okay, so this multiplication is these two, right, and then this is going to be repeated as is, plus, so let me write it there, plus S square CC1 R1 R2 plus SR1C plus S square C C2 R1 R2 plus S GM7 R1 R2 C. Okay, so this is left in the denominator, and the numerator is multiplied by 1 plus SRC. So I would have, let's collect the terms. Okay, you have 1 plus S terms, right? Okay, so let's collect those terms, S terms. Okay, so let's collect the term of S with R1. So S with R1, this one. Okay, S with R1 is R1 into C1, R1 into C1. So this term is done. Then SR1, just SR1. So here is another one, plus C, right? And then SR1 is over here also, plus, so I have accounted for this one and then plus this one. This is going to be GM7 R2, GM7 R2, and then C. So this is the Miller part, 1 plus GM7 R2 times of C. So this is the Miller capacitance, right? So this is the first term. Next is, let's look at other terms. So this is also accounted for. Let's look for the term with S and R. So next is S and R is over here, RC. So SRC will be there. So there is going to be CR here. So this accounts for that term. Okay, other than that, let's collect the term of R2, S with R2. So this is S with R2, so that will be left with C2, S with R2. So this is done. S with R2 is this also, C, right? So plus C. Okay, so this whole thing is S terms. So I have done all the powers of, how about this one, R2S. So this is done, C, and this is done. Okay, so now I'm only left with the square terms. Okay, so let's collect the square terms. S is square. Okay, let's collect the term of R1 R2 with S square. So first is this one. So this one is going to be R1 R2 times of C C2. So this is accounted for. Again, this one is also here, R1 R2 C1 C2. So there is C1 C2 here. So this is accounted for. Now this is the one, another one. So S square with R1 R2. So this will be C C1. So this is cyclic multiplication, as we talked earlier, right? So this is just the cyclic multiplication. So this is one term, okay, plus let's look at the other S square terms, okay, and let's look at S square terms with, so there are two more terms with this S square. Okay, one is this one, other is this one, right? Okay, R2 C2, yeah, this term. So one term is going to be C C2 R R2. So this is the term, and another term is this one, which is plus of C1 R1 RC. So these are S square terms, and let's do a S cube term. Okay, so there is only one S cube term which is left out, which is C1 C2C R1 R2, isn't it? So that's the S cube term. Okay, now in the, so this is the denominator. What happened to the numerator? I have to multiply this with 1 plus SCR. Okay, so let's go to VO by V in over here. So what I can write VO by V in, I will write here VO divided by V in, which is AV, is minus GM4 times of R1 this is first gain, GM7 times of R2, isn't it? GM7 times of R2, right? And then I have the numerator as this term, where I will multiply this with, okay, so this SC will come to the top, right? So SC divided by 1 plus SRC, isn't it? Minus GM7 is taken out, right? So times of, so GM7 is taken out, so GM7 is taken out, so here it will be GM7, right? And then I am going to multiply this with 1 over SRC. Is that correct? Isn't it? So this is there, divided by this denominator I'll put as D. Okay, so I have AV is equal to minus GM4 R1 GM7 R2, and I'll just multiply in, I will have SC over GM7 minus 1 minus SRC, isn't it? Divided by the denominator. So I am going to have minus GM4 R1 GM7 R2 times of, now in this case if I take the terms common, so I would have, okay, so if I didn't have a minus term inside, if I put this minus term as positive, then this will become 1 plus SC common, right? And this is going to be 1 over GM7, isn't it? Okay, minus SC common, because this has become minus 1 over GM7 minus just 1 second. So I have SC common, right? So I have 1 over GM7, and this is minus 1. Okay, just write it this way. Let minus be there at the output. So I have minus 1, and I have minus SC common. So I would be having minus 1 over GM7 here, and there will be R over here, isn't it? Let me verify. Minus SCR minus plus SC over GM7 minus 1, correct? Okay, divided by denominator, so we don't know what is denominator till now. So let's take this minus sign inside, doesn't matter. GM4 R1 GM7 R2, so these are the two gains, 1 plus SC R minus 1 over GM7, isn't it? Correct. Now let's put the denominator. So the denominator is going to be this big term, so I'm going to write very small, 1 plus S times of R1, right? R1. So this is the pole because of the input, which will be C1 plus 1 plus AV, right? 1 plus AV is going to be R1 GM4, isn't it? No, R2 GM7, sorry. R2 GM7 times of R2 GM7 times of C. Okay, so this is there. So this is the Miller pole due to Miller capacitance C, isn't it? So that you can see that plus CR plus, so this will be the RC time constant plus the output node R2 plus R2, and then when you refer the C to the output, it will be C only. So you will have C2 plus C. So this is the pole due to the this is the pole due to the output node plus S square. I'm going to throw out the S cube term, so I am just going to have S square term, which will be R1 R2 times of cyclic multiplication C1 C2 C1 and then C2. That's cyclic multiplication plus two terms as it's C2 RR2 C1 RR1 C2 RR2 plus C1 RR1. Okay, and I have thrown out the cube term. Okay, so I have expressed this as AV is equal to AV0 times of 1 plus S over omega Z divided by 1 plus S over omega P1 plus S square over omega P1 plus omega P1 into omega P2. Okay, so now let's separate out the poles. Okay, so first of all I'll find out omega P1. Okay, so omega P1 from this expression is going to be equal to the S term, right? So is 1 over omega P1, so omega P1 is 1 over that, 1 over R1 C times of R1 C1 plus 1 plus GM7 R2 times of C, okay, plus RC plus R2 C2 plus C. So this is the first pole, and in that the dominant component is this, right? So I will just replace this with equal to approximately 1 over R1 R2 GM7 C. Okay, so this is going to be my first pole. Okay, so this is pole 1, the dominant pole, and that is because of the Miller capacitance C. Okay, the next is, look at the second one, which is omega P2, right? So now omega P2 would be, if I multiply this term, or rather divide this term with R1 R2 GM7C. Okay, so it will be GM7C. R1 R2 will cancel with the denominator, and I will be left with this cyclic multiplication, isn't it? Okay, so what I have common here is R1 R2 GM7C R1 R2, right? So what I will do is I will divide by R1 R2. So I will have C1 C1 C2 C2 C. So this is the cyclic multiplication, right? Plus I have to divide by the remaining one. I have to divide by R1 R2. So R2 will cancel out R1. R by R1 C2, isn't it? Yeah, R by R1 CC2, and similarly I will have CC1, R by R1 CC1 plus R by R2 CC2. Am I right? R1 R2, just one second, R1 R2 will cancel out, wrong. So this will be C2 and this will be C1. C1. Okay, so now this can be simplified. right? So basically I can, this is going to be a big term, this is going to be a small term, so this would be approximately equal to gm7c. so this c I will take in the denominator, so I'll have c1 plus c2 and then c1 c2 by c, and if c is much larger than c1 c2, then because it will obviously be, so this term will be 0. So this would be approximately equal to gm7. So I am forgetting one thing, this is minus, so this is on the left hand side. Okay, so that's why I have to put here minus. So this will be minus gm7 by c1 plus c2. Okay, so this is going to be omega p2. Okay, or rather I'll put a blue thing. So this is pole number 2. Pole 2. So I have got pole 1, which is a dominant pole because of the Miller capacitor C, and pole 2, which is going to be the second pole due to the input node, right? Sorry, due to the cyclic multiplication. gm7 c1 c2, yeah, because the output pole is going to be in terms of S only, right? So that's a wrong statement. Okay, anyway, so this will be my second pole. Now what about the 0? The 0 is going to be, okay, so in this case it will be S over this, so 1 over that. So this is going to be the right hand side 0 will be equal to 1 over, this is simplified over here, 1 over S times of R minus 1 over 7. 1 over S times of R minus 1 over gm7. Okay, so this is my 0 it will be, so this is my 0. Now if R is smaller than, 1 over gm7, then okay, there will be a minus sign here. Then okay, then this, if R is less than 1 over gm7, then the 0 is on the right hand side plane. Then 0 is in right plane. Okay, now when R is equal to 1 over gm7, then 0 is, so this is your compensation, right? Then 0 is at infinity, right? And let's say R is greater than 1 over gm7, then 0 is in the left hand plane. 0 is in left plane. Okay, so now when the 0 is in left plane, let me equate to second pole, which is over here, right? So gm7 over c1 plus c2, okay, is equal to the 0, right? Where is the S term? This is not a S term, this should be C here. Mistake. This should be C. Okay, so now let us equate to this 1 over C R minus 1 over gm7. Okay, so this is, I am cancelling, so I am cancelling the second pole, C and C, cancelling WP2 with WZ. So at this point the R value I have to find out. So I'll cross multiply. You have CRGM7 minus of CR is equal to C1 plus C2, isn't it? CR minus, so I'll cross multiply it, right? So CR into GM7, and this will be C minus C. So I did a mistake here, just one second. So the first term is going to be CR GM7, the second term is going to be C over GM7, so it will be just C. Okay, so now I have R GM7 C is equal to C1 plus C2 plus C. Then if I divide R by GM7, just one second. So this will be R is equal to C1. Okay, so 1 over GM7 I can take common. Okay, so 1 over GM7 common, and then I'm going to do 1 plus C1 plus C2 divided by C. So if this is a condition, then I have cancelled the second pole. Okay, now so this is one way. Now if you increase R further, then the 0 will come between pole 1 and pole 2, right? So that's going to happen. Now let's consider some more things. Okay, that one of the thing is unity gain bandwidth of a OpAmp. Unity gain bandwidth, where the or UGB. Okay, so this is a point, this is the frequency at which the AV becomes 1, right? So let's have AV written as AV0, right? So we have AV0, right? And let's assume that 0 is far away from the first pole, so only first pole is considered. Okay, so let's consider only first pole. So I would have R1 R2 GM7C S. Okay, AV0 1 plus R1 R2 GM7C S. Is it? This is just the first pole, right? R1 R2 GM7C. Okay, and let's assume that this number is much larger than 1, because S goes up, right? So I'll have AV0 times of S R1 R2 GM7C. And what is AV0? Let's put it back here. AV0 is nothing but GM4 R1 GM7 R2. So GM7 cancels out, R1 R2 cancels out, so I am left with GM7 over S. So S is, this case is omega, let's put this omega UGB. Okay, omega UGB times of C. This is equal to 1. So then unity gain bandwidth UGB is equal to GM7 over C. So this is our unity gain bandwidth, correct? So this is our unity gain bandwidth. Okay, so the next thing which I need to look at is the slew rate. Correct? Okay, so slew rate. Okay. Slew rate. So slew rate of an op-amp is going to be dVo divided by dt. So slew rate positive. So when you go up, so when it is pulled up, when the output node is pulled up. So how is the output node pulled up? The output node of an op-amp is pulled up by this current, the current which is here. So I out, right? Okay, so that would be I out by C, because the C is the only capacitor which is being charged here, right? Okay, so that's one. And if you want to negatively charge it, SL minus will be again dV out by dt, right? dV out by dt, and that would be by the tail current. So basically this current is going to charge this capacitor in the reverse direction, so it will be entire tail current charging it. So that will be I tail by C, right? So basically that concludes what an op-amp is, right? And then you can do various modifications of op-amp. But now the point to note here is this op-amp is not going to drive any resistive loads, okay? Because if it drives a resistive load, okay, so so if this op-amp drives a resistive load, what's going to happen? This stage is going to starve of current, because the load will take all the current. So the current which is supposed to flow to bias this common source stage will be swamped by the load RL, and that would result in lowering of its gain. So this op-amp, two-stage op-amp, is not good for driving a resistive load. So for that you would have to put here a source follower. So in that case it becomes a three-stage op-amp. So in the next session I will discuss source follower, its frequency response and stability, because that has a complex pole which can cause ringing. So then you have to load that with a C enough, or RC enough, that it doesn't have a lot of overshoot, right? Or the ringing is minimum. So we will look at what is the condition for, you know, a certain overshoot, right? So right now the op-amp has got two stages and it can drive capacitive load. Now if you want a op-amp to be driving a resistive load, you have to put a source follower, so you have to have a three-stage. Now usually when you talk about inverting and non-inverting amplifiers and feedback resistors, you have to have a third stage, because your feedback is a resistive feedback, right? So that's why you are supposed to use an op-amp with three-stage, not with the two-stage, right? So that's the basic mistake a designer does, is he tries to use in feedback configuration an op-amp with two-stage, and it's not going to work. Okay, so with that I close session 13, right, on op-amp high frequency response. Thanks a lot.